Something going to do. Here we go. Welcome to the ASVs January Astro Talk. This month we'll be from Dr Tsana. Alright. Dolichva. Close? Close. She'll be giving us a talk titled Using Chemistry to Understand the Orbits of Dying Stars. Before we begin, though, I'd like to say in the spirit of reconciliation, Astronomical Society of Victoria acknowledges the traditional custodians of the country throughout Australia and the connections to the land, sea, and community. We pay our respect to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander people today. Dr Tsana is a research fellow at Monash University, currently holds a DECRA fellowship from the Australian Research Council. She studies dying stars, and especially the dust and molecules that form around them during their death throes. Although she comes from Melbourne, her studies have taken her around the world prior to taking a position at Monash. She previously worked in Belgium and completed her PhD in Sweden. Pretty accomplished. Following her talk, though, we will be graced with a tour of let's read that again. Following her talk, we will be graced with a tour of what can be expected to see in the sky this month from ASVs own Stent. Let's go to Gent. But with weather looking as good as it is, as it has for a long time, if you never want to remember blue sky, I feel like we'll be like until the last few days. We're going to open the observatory, and we'll definitely be able to open it tonight because it's not going to get cloudy. But for now, I'll give you hand over to Dr Tsana Dolichva. Did I get that right?
Hi everyone, as Mike said, I'm Tsana Dolichva, and I'll be talking about using chemistry to understand the orbits of dying stars. Now, I realize there's a little bit to unpack in this title, so let's start with dying stars, right? So, when you think about dying stars, I think there's a fairly good chance that a lot of you possibly think of supernova explosions. That is not what I'm going to be talking about. And that is because stars that go supernova have to be massive enough to be able to go supernova. Stars like our sun never will. Basically, we can divide stellar evolution into two categories. What happens to the lower mass stars and what happens to the higher mass stars. So high mass will end up in supernova, and lower mass stars like our sun will, well, do something else, which I'll explain shortly. So in this diagram, the sort of cutoff is 8 to 10-ish solar masses. So stars that are 10 times as heavy as our sun or more will explode, and stars that aren't won't. They go through the red giant phase and eventually end their lives as a planetary nebula. So throughout this talk, I hope to make you understand that just because supernovas are slightly more exciting and dramatic, the other kind of stellar deaths are still interesting. So here I said 0.8 to 8 solar masses, roughly. I mean, there's a few variables in there for where the upper and lower cutoffs are. But that's what I mean when I say stars like our sun. So in that kind of mass range. And overall, in our galaxy, the sun is pretty average. The actual average mass of a star in the Milky Way is 0.9 solar masses. So 90% of the mass of the sun. So yeah, the sun's pretty close to average. So here is the set of classification of stars. I believe this is to scale with the radial sizes there. And the sun is a two-type star. And as I said, the more massive stars, dying in supernova, they also have much shorter lives. So live fast, die young. And then the less massive stars live longer and go through the red giant phase. And you'll see I put those arrows up the top. Their ends kind of overlap with the B region, and that is because B-type stars, some of them count as low mass, some of them count as high mass. I mean, well, you could say they're intermediate mass. But when people come up with labels like this, they're not really thinking about the physics. They're thinking about, what do we see? How can we categorize it? And then later we have to understand what that means. There's a lot of that in astronomy. You see something, you try and find a category for it first, and then later try and understand what it is. So anyway, our sun, familiar with it, especially if you were outside earlier today. One solar mass, that's the mass of the sun, just to be absolutely clear about that. And the other thing I want to explain at this point is why the sun shines. Right, so the sun is powered by nuclear reactions inside its core. It's mostly made up of hydrogen, and in its core, gravity from like how heavy it is, which is a 2 followed by 30 zeros kilograms. Like that's enough gravitational force to smush the hydrogen atoms together, and they form helium, and that's the main reaction. I mean, it's a series of reactions, but that's the main thing that's going on inside the sun. And it's creating a lot of energy, and that energy eventually escapes, and it's like the light we see from the sun. The sun is large, but it's not infinitely large. And eventually, it's going to run out of hydrogen to fuse. And, well, then what happens? Then it begins its next evolutionary journey. I can use this image a lot, I think it's quite helpful. So if we start with the sun down here, once it runs out of hydrogen, it will expand a bit. It will go on to fuse helium in its core a little bit, so that means it will eventually have sort of enough energy and pressure to fuse helium, which doesn't create as much energy, actually, but eventually it also runs out of helium. But while it's burning helium, it's on this red giant branch, so it expands a bit. This is almost to scale, except the planetary data very much is not to scale with the other images here. But close enough. Eventually, once it's also run out of helium in its core is just made up of carbon and oxygen, so mixed depending on the star, and it becomes what is called an AGB star. I will shortly explain why it's called an AGB star. It's a terrible name. And it's another one of these, let's classify it this way and not worry about why it's like this until, decades later. But during the AGB phase, which stands for asymptotic giant branch, during the AGB phase, the star expands even more. And that bit is actually not quite to scale either. The star will expand up to a radius of about 180. So an AU is how far the Earth is from the sun. So when the sun goes through this phase, it will swallow the Earth. Maybe even approach Mars, depending. We're not 100% sure exactly what dictates how big they end up. But something like that. And in this case, the surface of the star is quite unstable. That's kind of why it's expanded, but it actually pulsates a bit as well, so it gets bigger and smaller. So it's a variable star, which is perhaps many of you are familiar with. And during this phase, partly because of the pulsations, partly because it expands so much, it's also cooled a lot, which means when it expands, it sort of throws off some material, and some of that material turns into dust. And then radiation pressure from the star. So the star is still pretty bright. It's a lot cooler, but it's 7,000 times brighter than the sun, maybe. Again, depending on the star. So that's a lot of radiation. And what we call radiation pressure, which is basically lots of protons colliding with the dust, gives them a little bit of energy, imparts a bit of momentum, pushes them outwards. And then those dust particles fly with gas that hasn't formed dust yet, or maybe never will, and drags that outwards as well. So what we get is what we call a stellar wind. And we sort of also, when we observe it, we kind of take a snapshot. So it's all moving outwards from the star, but in a snapshot, what we see is a certain stellar envelope. So sometimes we use those words interchangeably. But these stars throwing off a lot of dust. So, eventually they throw off all of their outer waves and they become a planetary nebula, which is got nothing to do with planets. It is called that because it was bluish and so was Uranus. So, why is it called an asymptotic giant branch star? This is the Hertzsprung-Russell diagram. The slash down the middle is the main sequence, and that's where most stars spend most of their lives. And going up where it says giant, so this one is not a very scientific HR diagram, but it has nice labels. That's roughly where we're looking. On the left, we have the a more scientific HR diagram showing the path of evolution, or how a star like our sun, a one solar mass star, moves around the HR diagram during its life. So it starts on the main sequence. So it starts where the other one says sun. And then it moves up the red giant branch, and then down again, and then up the asymptotic giant branch, which is called that because it gets close to the red giant branch, and astronomers are often not very creative. So that's where the name comes from. So back to this though. So the thing on the right is a planetary nebula that it happens to be also my favorite planetary nebula, the Helix Nebula. And I think it's the biggest, certainly one of the biggest. There are a lot though, and they're really quite pretty. Here's a nice compilation. These are all slightly the wrong color on the screen, but never mind. But they're all to scale relative to each other in terms of how they appear on the sky. The Helix Nebula isn't here because it's so much bigger. And yeah, so that's what I mean when I talk about dying stars. So the other part of my title mentioned chemistry. So I'm now going to introduce the ideas of astrochemistry. So, what is astrochemistry? I was literally in chemistry in space. It's not this kind of Bunsen burner chemistry. When we're talking about gas and molecules being thrown off by these stars, although that's a really dense environment by space standards, it's not very dense by human standards. And pretty close to the star, aside from the temperature, the pressure is like an atmosphere, as in an Earth atmosphere, what we are all currently breathing. I mean, you shouldn't breathe it, you will die. Lots of reasons, but it's already a verified environment, even in the densest parts around these stars. So with astrochemistry, what we do is we look at molecules, we look at where they form, we try and look at how they form, how they interact with each other, and how they go on to form dust grains. So take a moment to explain why dust grains are important. I've already mentioned them once, but these stars, the AGV stars, about half the dust in the universe forms from these stars, or around these stars. I say around half because it depends a bit on the dust, but supernovas contribute as well, or massive stars. So why that matters is, I already mentioned fusion happening inside these stars. While they're on the main sequence, the fusion is not very exciting, and making helium not that exciting. Carbon and oxygen, more useful, more interesting, more essential to life. But while they're AGV stars, because of sort of the unusual environments inside them, they're all a bit more chaotic. There's like different regions that are hotter, and there's pulsations, and it mixes things up to the surface, all this sort of thing. A lot of other elements are also formed. So you've probably heard the idea that we all made of star stuff. So this is some of the star stuff we're made of. So the dust, in particular, that leaves these stars, will go on to form the next generation of stars and planets. And understanding how planets form is sort of one of the bigger picture questions that we're looking at. But, so molecules. Molecules are made up of like a few atoms. Well, they can also be bigger, but the ones we look at in space are mostly quite small because they're really easy to see. But actually, how can we see molecules in space? Because, it's not like we can see individual molecules on Earth. They're all around us. Water is H2O. This one. Air is made up of molecules. So how do we see them in space? And the answer is, the unhelpful answer is quantum mechanics. The slightly more helpful answer is what I'm going to explain now, which is, so here is a molecule. This is hydrogen cyanide. There's a lot of it in space. not a good molecule to encounter on Earth, but far away it's fine. And it's a good example for this because it's a nice straight line. And it's a straight line made up of 3 different atoms. And because it's made up of 3 different atoms, when a photon or a light wave of the right frequency passes by, it can make it spin. Did that just spin? Okay, cool. Sorry. And in this case, because it's a straight line, there's kind of only one axis that it can spin on. I mean, if you turn it around, you're just looking at it from different sides, it's not a different thing. Spinning this way doesn't count. It's not changing, because the light is electromagnetic radiation, and there is a little electric dipole across this molecule because it's made up of different atoms, hydrogen, carbon, and nitrogen. And the light kind of interacts with that electric field, and that's what makes it spin. Whereas in the other direction, there's no change. If the light passes it this way, that doesn't count. This molecule is uranium, also maybe some people are familiar with. And I've included it because it's a nice example of a molecule that you can spin in 2 different ways. And those 2 different ways that it can spin require different energies of the light that's passing it. And one more is water, which, A, I included because I don't know what it is. But B, I've included because there's actually quite a lot of water in space. I used to make a joke that it's everywhere except Mars, but I don't think that's Mars. And it's this little V shape, and that actually means you can spin it in 3 different directions with different energies and get, different energies in 3 different directions. And this idea applies to all sorts of molecules. So, the faster the molecule spins, the higher the energy. But because it's very small, and quantum mechanics applies to it, there's only very specific energies it's allowed to have. And that's at the lowest energy, the light makes it spin once, the next energy is twice as fast, loosely speaking. So it's in units of that, which means that when we observe with a radio telescope, something like this, which is called a spectrum, we get these bumps, and because of studying these molecules on Earth, we can work out what molecules each bump corresponds to. So each bump is comes from. Backwards. So each bump comes from these molecules. There also you'll notice, especially I guess looking at this one, it's not infinitely thin, and that's because molecules of water around this particular star, or most of the stars I'm talking about, are expanding outwards. So we see some coming towards us, and some moving away from us, and some moving outwards, which is not moving relative to us. And for that reason, we get this wide line. So it's like the Doppler effect. So the molecules coming towards us have a slightly higher frequency, and the molecules going away from us have a slightly lower frequency. So they get spread out over this line. And so I'm a radio astronomer mainly, so I put a little clip out there. And the telescope that I have used the most recently is the ALMA telescope in Chile. And it is not one telescope, a telescope array. So ALMA stands for Atacama Large Millimeter/Submillimeter Array. And it's made up of 64 dishes and white. Basically, the bigger the telescope, the better. However, we have some engineering difficulties in making a telescope, for example, 16 kilometers in diameter. So what we do instead is there are lots of little telescopes and add their light together in a fancy supercomputer way so that it acts like one giant telescope. There are some limitations to this. It's not perfect. It's more or less because there's gaps between the telescope. There's some things you can't see, but when we're looking at small details, this is the way to go. So ALMA actually just in December celebrated its 10-year anniversary. And when ALMA came online, or got first light, as you say, what we in the AGV community were excited about was finally being able to measure the extent of these molecular envelopes around these stars. Right, so the molecules expanding away from the star. If we can tell how big they are, like the extent around the star, we can better measure how quickly the star is losing mass, which helps us understand its lifespan, or especially the lifetime of the AGV phase. So that's what we were expecting. Right, that's nice, but that's not exactly groundbreaking. This is what we got from the first AGV observation with ALMA. So this was observed because this outer circle, the yield is there. This was an event that happened 1,000-ish years ago to this particular star, and they wanted to study this phenomenon. What they were not expecting was this spiral inside of that outer shell. So the outer shell is something called the thermal pulse. It happens to these kinds of stars every 10,000-ish years, or tens of thousands of years. But that's got nothing to do with the spiral. So that was a bit of a surprise. What is this spiral? Well, the only thing that really makes sense is that there's another star, a companion star, somewhere near the center that we can't see. And it has to be one we can't see, because if we could see it, we would have already seen it, if you see what I mean there. But this is a very dusty star, so the dust has to be obscuring whatever it is. We also don't know how big this companion is, as in, is it a red dwarf, is it a solid known planet, as in gravitationally, this is too much for it to be a planet. Is it a red dwarf, is it a white dwarf, is it a brighter star? It also can't be too hot, because then it would destroy a bunch of molecules. I have to say, the specific star, I don't know the answers to that, because it's not the star that I'm mainly going to be talking about, but these are the sorts of questions that were raised. So then we thought, well, we should look at more AGV stars. And in between this and what I'm about to show, there were some other observations, and they kind of mainly showed not exactly the same thing, but like a lot of weird shapes, like what I'm about to show, which does not look awesome on the screen, I'm sorry guys. But you can see there's some funny shapes. This one's kind of got like an hourglass thing going on. The one on the other side looks a bit like a rose for some reason that we don't really know. And in this image, the blue light is coming, the blue colored stuff is coming towards us, the red is going away from us. And this is all carbon monoxide, and so is the previous slide. Right. So this is one of the most ubiquitous molecules that we can easily observe. It's the second most abundant molecule around these stars, generally speaking. The most abundant is hydrogen, like H2. We can't observe that very easily, so we use this. It's very abundant because oxygen and carbon are the third and fourth most abundant elements, I should say, in the universe, but also around these stars. So when they bond, the bond is very strong between them, and it's quite hard to destroy. Which means that when we're looking at the gas generally, this is the best thing to look at, and we see it further out from the star than other molecules. And I will now focus on this star, which looks terrible here, but we know better image is coming. W Equulae. So W Equulae, it's a long period variable in the constellation of Aquila, hence the name. Long period means the pulsational period, so the brightening, darkening cycle is 490 days, more than a year. We have a lot of observations to the star, going back to 1905 with ASVs, that's the American Association of Variable Star Astronomers, American observers. So it's a fairly bright star, especially at peak brightness, and it's been known for a while, and from the 60s, point out that it was actually a binary star, which contributes a little bit to it being brighter. So, as I will sort of explain, not that much brighter. Also, is that dot in the constellation? Sorry, we'll just move the arrow up here. So it's a binary star. The primary, the brightest star, is an AGB star, and that's the star that I spent a disproportionate amount of my career studying. Not the only star, but it's I've written most papers on it. And the second star, which is less bright, is very similar to our sun. So I'd say our sun was a G-type star, and this one is an F-type star, but it's the edge of the F. So it's almost G. It's very similar to the sun. Tiny bit hotter than the sun, tiny bit bigger than the sun, but like it's a rounding error, basically. So, in 1965, telescopes weren't actually good enough to distinguish the two stars because they're quite close together. And it wasn't until the Hubble Space Telescope that we had like good enough resolution to see the two stars. And there was actually also an earlier observation of Hubble in 1993, but that was before the Hubble Service mission. I'm not sure if you've heard about it. When Hubble first launched, there was something wrong with the mirror, they had to go fix it. And so the earlier data was just not good enough for this. It's not good enough for what I'm doing. Which is trying to work out how the two stars are moving relative to each other. So we got more recent observations with SPHERE, which is an instrument on the very creatively named Very Large Telescope, also in Chile, different place there. And I hope you can see the yellow cross on the screen there, but that's where the other star is. They're plotted on the same scale. It's a bit hard to compare them when they're side by side, so plotting just the stars together. Here, the red star is the AGB star, green is Hubble, and yellow is SPHERE. You see they moved a little bit, but like, really not that much. So in 15 years, tiny amount of movement. What that tells us is that the orbital period, so how long it takes the two stars to orbit each other, is very long. Very long, like 1,000 years. So, too long for us to, well, for us specifically in this room, to sit here and observe it and work out what the orbit is that way, which is what we kind of do for a lot of stars. But in those cases, those stars are close together, usually, and or perhaps more massive. And here we've got a long orbital period. Okay, so in terms of sort of the binary star, I should also say that it's kind of far enough away that it's the second star, the sun-like star, shouldn't really be changing what the AGB star is doing. Maybe it is changing what it's doing, but we couldn't really work out why for the time. But because this is an AGB star, there's not like that many AGB stars in the galaxy. I mean, there's like hundreds compared to hundreds of billions of stars in general, so they're relatively rare. W Equilate is relatively nearby, so 400 parsecs might sound like quite a lot, but on the scale of things, is basically next door. I've said that it's relatively bright. It also conveniently is fairly close to the equator, slightly in the southern hemisphere, but close enough that it can be observed from the north and the south, which is pretty helpful. We've been studying it as an AGB star because it's relatively dusty, and it's part of an even rarer subclass of AGB stars, which are transitioning from being oxygen-rich to carbon-rich. So I mentioned briefly before that while stars are on the AGB, elements are still being formed inside them, just in a sort of more complicated way than on the main sequence. And that's kind of like what's happening here, as in all stars are oxygen-rich when they get to the end of their lives. And during the AGB phase, more carbon is created, eventually mixed up to the surface. And so they go from being oxygen-rich to carbon-rich. And this just means more oxygen than carbon, or more carbon than oxygen, really. And for W Equilate, the AGB star is in between. So it's roughly the same amount of carbon and oxygen. So in general, you want to understand how the AGB evolutionary phase works, and understanding that transition phase is part of that. We've been studying it a lot. So the nicer version of the image I showed you before has kind of all the information. Still quite small, there's a big one on the next page, just bear with me for a moment. What we can see is a lot of details about the carbon monoxide. We can see which bits are coming towards us, which is like the top line, and moving away from us, which is the bottom line. I mean, left to right, top to bottom. And the red squares in the middle are, well, the three images that are averaged on the next page. But the center one is roughly the velocity of the star itself. So the star itself is moving away from us a little bit. This is just because of where we are in the Milky Way, where it is in the Milky Way. That's not significant in a physics way as far as I'm concerned. But the larger image, I promise, you can see here, you can more or less see here, a lot of kind of chaotic arcs and things around the star. The bright bit in the center is where both the AGV star and the other star are. I didn't mark them because they'd be so close to each other, you wouldn't really be able to tell them apart. But yeah, so we see all these sort of shapes and we want to know why. You know, what has caused this? It's not particularly obvious that it should be the second star. It is the second star, but it's not obvious exactly how. So with our observations, so on the previous slide I showed you all of different stars. Looking at just this star, this is sort of, I mean, different zoom levels and things, the full spectral coverage. So all the different frequencies we covered from 212-ish to 266 or something like that. And there's some gaps because we're targeting what we thought would be interesting molecules. And then, you get some bonus things, which is nice because a bonus thing is actually the crux of my talk, and I'll get there in a bit. But in total, and it's hard to see in this plot because of the thickness of the line, but more than 110 molecular lines were detected towards this star, which is a lot. It's not the most in the whole Atomians in the large program. It's not the most in the whole Atomian sample, but certainly not the least either. So in studying this, it's a lot of data. So each one of these lines is this much information. So this is terabytes of data. I looked at all of the lines to see which ones are doing something exciting. And I'll start by showing you some images of some common molecules. So these are silicon monoxide, silicon monosulfide, carbon monosulfide, and hydrogen sulfide cyanide, which is the long one that I showed you before. So what's interesting here is that, generally speaking, when we look at molecules around stars, I mentioned before they're all expanding away from the AGV star. It should be like a roughly spherical shell. Maybe there's another star sort of stirring it up, making a spiral like we saw for that other star. But generally speaking, we expect to see roundish blobs. Alright? Maybe roundish blobs with a spiral in them, but roundish blobs. This might look like a roundish blob to the untrained eye. However, the red star in the center of each box is the location of the AGV star. And as you can see, the blobs are not symmetric around that star. So what we're seeing here is quite interesting. The second star, the sun-like star, is the little yellow one, down and to the right. That star, the UV photons from that star are energetic enough to destroy these molecules. So this is something that we, in principle, knew happened, and in general, that's kind of what destroys molecules. When they get far enough from the sky, something we call the interstellar UV field, which is just light from all the other stars in the galaxy, eventually destroys them. But here we're seeing a specific nearby star destroying a bunch of molecules, which is cool. It's not, like I said, we kind of expected it, but we haven't really seen it before. So this is not really the groundbreaking discovery itself. What was interesting was when I looked at the next molecule, which is less common. It hasn't been detected very much, only towards one other star. And this is Sint, silicon nitride. Now, well, you can at least see the black outline here. The colours look better on my screen. But you sort of see it forms not a roundish blob, but kind of a triangle. And that's weird. Like why is it doing that? The other ones were, there was more stuff over here and on the other side, where it was being destroyed by the star, there were still molecules over here. So why is this such a kind of narrow wedge, triangle, whatever you want to call it? Studying it in more detail, if we kind of rotate it like this, so that the triangle is pointing up, and then look at which bit, so this is all of the silicon nitride light in this image. That's just all of it added together. If we look at which bits are coming towards us and which bits are going away from us, we suddenly get an interesting picture. And that is this kind of an arc. Like, that's also pretty weird. There are some molecules that just form at a specific distance from the star, but they still mostly form in all directions. You know, with maybe some like general blobbiness, but roundish blobs. Generally expect roundish blobs. So why is there an arc on one side of the star? And this is where astrochemistry comes into it. So at this point, I conferred with my colleague who runs theoretical models of chemistry in space around these sorts of stars. And what she said is that Sint, silicon nitride, mainly forms if there's an extra source of UV photons. So why is that? That's because the UV photons are needed to destroy the other molecules. So for example, SiS, silicon sulfide, and ammonia, which is NH3, nitrogen, 3 hydrogens, to free those up to be able to make Sint. Because those other molecules are much more common and much more easily formed. So okay, we need a source of UV photons. We have one, but it's on the other side. So that doesn't, like this did not form those molecules like at this moment in time. That doesn't make sense. Eventually, what we worked out was that this kind of scenario. So, before this we were assuming a much rounder orbit, but if we consider a very elliptical orbit, or what we call an eccentric orbit, then it all started to make sense. So on this orbit, at some point, the Sun-like star will pass very close to the edge of the star. So if we kind of see it going clockwise the way I've drawn it here, and this, by the way, is just looking down on the orbit, it really is that squished. So when that star is in that dense inner region close to the star, close to the edge of the star, where there's a lot of gas and where it hasn't expanded outwards very much, which means the UV photons from that star will collide with a lot of molecules, cause a lot of extra reactions, then that star passes through pretty quickly and just in like a line, and creates a bunch of Sint and a few other molecules, which I'm not trying to do a bit less aesthetically pleasing. And then the Sun-like star goes on its way, and the Sint, along with everything else in the stellar wind, just continues expanding outwards. So what we end up with is that arc that I showed before, and it's an arc seen edge on only one side of the star. That's pretty cool. To understand this scenario a little better, we also ran some hydrodynamic models, which will hopefully, they're running in synchronized. So face on, as in the orbit is, you're looking down at the orbit, and the other one is you're looking side on to the orbit, and the one further away from me is what's actually happening. And these sort of circles that form every time the stars pass each other explain some of those arcs in the observation that I showed you earlier. So that's nice. I have slightly jumped to the solution without explaining some of the points, which is that when we're understanding orbit, we need to know the masses of the stars. Or we work out the orbit through observing two stars that are quite close together, and then work out their masses, or their combined mass. That's not possible here. As I said, the orbit's very slow. We need to know the masses to be able to work out the orbit. So for the Sun-like star, it's quite easy. We know it's that type of star, and therefore we know that it is slightly more massive than the Sun. For the AGB star, it's a little bit harder. And indeed, instead, what we need to do is look at what kind of elements will form inside the star. And some of these elements, and actually their isotopes, specifically the oxygen isotopes, depend on the mass of the star. So the rare oxygen isotopes, how much forms of each one. So 16O is the one that's everywhere that we're breathing right now. But there's also 17O and 18O. They're not radioactive, but they're much rarer. And how much of each of those form depends on the mass of the star. So through those observations, we can try and work out what happened. And that they form later in the star's life after the main sequence. So more on the red giant branch and at the end of the red giant branch. So that's the main thing I wanted to talk to you about today. And just to give you a little bit of a look at what I'm planning to do in the future, it's looking at more binary AGB stars. I'm particularly interested in how orbits change things, because to me it looks like binary companions, when there's a second star, causes more dust to form. And that changes how long the AGB phase will take. And that changes stellar evolution. So that's kind of important to know. The oxygen thing, the oxygen isotopes that I just mentioned, which we can use to find masses, actually only work on the lowest mass stars, up to only 4 solar masses. Above that, we can't work out their masses. So if we look at other isotopes, perhaps magnesium, that's something that would be interesting to look at. So that's where I'm hopefully going in the future. So W. Clay, the paper that I talked about today, was actually published on Nature Astronomy recently. If you follow that link, you should be able to see the full paper without a paywall.
Do you have any questions? Oh, I need you to ask a question.
Thank you, Tsana. Very informative. I have 2 questions. One is related to the process of the UV killing off some of the molecules.
Yeah.
Why specifically UV? Is it the frequency and the energy which is compatible with knocking out the alpha electrons? And the second question is related to the accuracy of your results, coupled with the distance, the error rate, and also the allowing for the gravitational redshift.
Do you get that?
Yes. I'll start with gravitational redshift, which is not especially relevant in this case. There's no black holes in the mass of W Clay, it's all good. For the accuracy in terms of the orbit, I worked out, yes, there are definitely uncertainties. I actually worked out a set of orbits that agree with the observations, but they're all very eccentric, highly elliptical, and they all have a period of about 1,000 years, and the periastron, when the 2 stars pass each other, well, that was one of the constraints, happened close to 200 years ago, a little less. And the orbit that I've shown here has an eccentricity of 0.93, where 1 is not an orbit and 0 is circular. So that was like one of the middle results, and I just chose to plot one of those. For your question about UV photons, why UV is because the light has to be energetic enough to break molecular bonds. So in this case, electrons, well, initially electrons are not especially relevant. The molecular bonds of SiS, silicon sulfide, not that strong. NH3, a bit stronger. And there is the step where we do need the silicon to also be ionized, so that is also knocking out an electron. And basically the UV is energetic enough for that to happen. This star, similar to our sun, is not the most UV bright, I guess, I'd say, star in like the galaxy. It's similar to our sun, but it's enough to destroy these molecules. It's not enough to destroy carbon dioxide, which has a very strong triple bond, and that requires a much hotter star, or for it to be like spread out enough that like one molecule gets hit by one photon at the right moment. That makes sense. Yeah.
Do we have another question?
If I can follow up with one thing, please.
Just a question on the different chemicals that you see. Is that all related to the size of the star or where it is on its evolution? So does it, chemicals change as the star gets closer to the end or the initial size of the star?
It's a bit of both. So a lot of the molecules I showed, let's look at these ones for example. In this plot, silicon, sulfur, and hydrogen are not generated in AGB stars. So when these elements are present, they're present when the star is born. So at some point, the start of the universe, we just had hydrogen, a bit of helium, tiny amount of lithium. And the first stars formed, fused more hydrogen into helium, helium into other things, and this process that goes on through the history of the universe. And yeah, so these lighter elements I'm talking about here, carbon, I said, is formed inside the star, so the older or the longer the star has been on the AGB, the more carbon there is. There's also these AGB stars are responsible for about half the heavier elements. Heavier being heavier than iron, and so there's some processes that kind of work in these stars that just kind of keep adding neutrons, and we kind of get heavier and heavier elements, and they add some neutrons, decay, add some neutrons, decay. So we get a bunch of things. We're not looking at those heavier elements here because there's not as many of them. They're annoying to observe in molecular form. Possibly they do not form molecules as readily sometimes.
Thank you. I have a very simple question. When I think of dust, I think of dust like in my bookshelf. What do you mean by dust? What's it made of in my stars?
In each of these stars, and a lot of our stars, there are two main types of dust. There's what we call silicate dust, which is basically sand, as in tiny ground up bits of quartz, not seashells, the other part of sand. And there's carbonaceous dust, which is basically soot. And that is actually basically soot. Like, not the bits of tree left in the fireplace, but the black stuff. So one of the things we're trying to work out in general is like exactly what the dust is. We know generally what the dust is, but we kind of don't know what shape it is. Like the crystals of sand on Earth, we can put them under a microscope. It's not complicated, but sort of how fluffy or how lumpy or smooth or whatever they are. We can determine some of that through observations, but not quite all of the details, and that's also one of the things we're trying to work out, because exactly how the dust works also helps us understand how planets are formed. Because the same dust is present in planet-forming regions or in planet-forming disks around stars. Don't have a picture of it, there are some really nice ones out there from our now. So we generally want to understand this dust.
Another question, we'll couple more questions. I'll come to you next, but I'm just going to continue my marathon. So I haven't got my mic.
I'm not even sure how to ask this question. Perhaps perhaps I'm not smart enough to answer this question, but you were saying that you're trying to work out what that dust looks like, similar to putting sand under a microscope. So we have access in our solar system to similar dust.
Okay.
The answer is yes, or at least sort of. So there are some meteorites that fall to Earth that had, like inside the meteorite, there were old dust grains that some other bits of stuff formed around. It's not my area, I'm not exactly sure why. It's a problem with the geologists. But we find inside grains that we're pretty sure came from around AGV stars. We call them pre-solar grains, as in they didn't come from when the solar system was forming. They drifted in from somewhere else. And we can study these. So we can work out a lot of things about those, but there is a limitation that they have formed through our atmosphere. So even though they're inside this bigger meteorite, things might have changed. And we also don't know exactly where they came from, so that makes it a bit trickier. There are some missions to get samples from asteroids and comets, and I mean, broadly speaking, those might also have some overlap with this dust, but it's a little harder to be sure, like exactly where it came from, this sort of thing.
We could have one last question.
Your future work, you would, correct me if I'm wrong, but you're looking at AGV stars, yes. And are you looking at binary stars again? And if so, I'm just curious, how many of those sort of systems are visible to our current technology that we can actually study with these type of techniques?
Okay, so that's a very good question. So I have a theory. It's like, see future paper in a couple of years. I have a theory that most of the AGV stars that we've been observing with our little older telescopes are like one dish, we're a bit biased with which stars we observe. So at some point there were these surveys, they identified which stars are AGV stars, people started looking at them, and they said, oh, these ones are quite bright, let's keep looking at the bright ones because we know we'll see something. So I'm pretty sure those are all binary stars. I mean, this is, like, don't quote me, but coming soon. But every single star that we've looked at with ALMA at high enough resolution to see, like, interesting shapes has weird, interesting shapes. Nothing is, like, a round sphere like it should be. Make it easier to study. Everything is some sort of special snowflake. And generally speaking, the way we explain these shapes is through a binary companion. Whether that's another star or a planet is unclear. And the really strange thing, like the reason I'm standing here saying this see a future work, and someone hasn't already written this down, is because we're not actually, like optically, with optical telescopes, being able to see these other stars. So I think it's because these stars are extra dusty. That's also what makes them bright, but there's more dust, there's more molecules because they're being dragged out more. But we don't. I need to do a bit more work to prove that. Basically.
Hopefully, thank you. Hopefully Jace has answered your questions today. Sandy. Thank you very much for coming and giving your talk tonight. Wonderful having you. Good creative tonight as well. And we're now going to jump across to Bill's stand for the telescope units. Just give us a tour of what's in the sky this month.
I have a mouse in here somewhere which I will be using as a clicker because I'm going to make Okay. It works. Tonight I'm going to be talking, it's the first of a series of talks I understand, so I'm going to be talking a little bit longer possibly. So the Thinking Grey I will be talking about this month. So I'm going to start by talking about the general conditions for stargazing at this time of year, and then I'll go on to talk about some star maps because everyone uses different types of star maps, and I'll talk about what you need. I think probably most of you know. Then I'll get down to what's in the sky, and I'll start with the moon because it's there. And then I'll talk about the overall sky tonight, tomorrow morning, and next month as it changes. Then I'll start. Hopefully, the more interesting part is the suggested targets to look for in the evening and the morning. And that's going to be planets, constellations, asterisms, clusters, doubles, nebulas, galaxies, and anything else I can think of. Then I'll talk about how to find other targets because everybody tends to look at the same stuff. So getting some new stuff in would be kind of nice. And then I'll finish off by talking about random other stuff to look at for this month. In my last work. Yes. But first, me. I hate talking about me. Before I talk about me, we are on the lands of the Bunurong and the Wurundjeri people of the Kulin Nation. The Bunurong people on this side of the river and the Wurundjeri people on the north side of the river. I am contractually obliged to identify myself as Dr Tsana. It's all his fault. I used to have a different name, but not anymore. I am a refractor guy. I am unashamed about the fact that I'm a refractor guy. I love refractors. Those new guys on the block, the Newtonians, like, I'm sorry. But, although I do have a confession, I am Newtonian curious. And I'm also an astrophotographer. And the thing you've got to understand about astrophotographers is we like to avoid all forms of human contact. When you go up to DSS, you'll see everybody around the observing field, and they're all sociable. And then you go past the roll-off, and then you go into the astrophotographic field, and you'll see 4 people standing there with their telescopes and their computers, and they're just sort of watching a little PhD through line background. So that's my dark side. I'm also a demonstrator here at Melbourne Observatory, so I'm going to be running from here up to the Tratan Sims, I think, to get it set up for tonight's observations. And I also work at the telescope factory in Tullamarine. I'm not going to talk too much about that because this is a non-commercial atmosphere. Okay, summertime. Stargazing is not so easy. It's nice and warm, which is fine. But sunset is a problem. Sunset's about 8:45 and it's dark enough about sort of an hour after that. By the time February rolls around, mid-February rolls around, it's going to get another 20 minutes or so of observation. Sunrise tomorrow is just after about 6:10 a.m. It's probably due like about an hour, maybe a little less beforehand, so you're going to finish at 5 a.m. What all this means is if you're a parent, grumpy young astronomer, you're going to have your kids up late or up very early, and small mammals become fractious, etc. You've also got to understand the mosquitoes. There are even mosquitoes in the gnomes up here. I'm a victim of that. So if you've got some spray, please spray yourself before you go into the dome. It's a good idea. With stargazing, generally speaking, when you get comfortable, have a bit of a rest with your eyes closed before you actually open them up, it's going to be, you'll see a very obvious difference in your ability to detect stars, particularly the fuzzies as well. Yes, you can use a phone app to find your way around the sky. I do. You'll need to turn it down to a minimum, otherwise you ruin that nicely organised adjustment device. Sky maps. Everyone uses different sky maps. I used to use Northern Star Atlas because that was in the 1970s and that's what we did. These days I use Stellarium. The real astronomers like to use cart seal, but I'm not a real astronomer, I'm a master photographer, so but it doesn't really matter what you do. The stars are kind of the same, so you know, it doesn't essentially matter. So now I don't know if you can see this. This is actually, what's that? Can we turn this light off? Yeah, you might talk about some very, very poorly. Oh, thanks. Just put it Oh, yes. Thank you. Okay. Let me stand over here. This is the sky at 10 p.m. tonight, facing north. Now, because I'm used to working at the LDSS, I generally like to stand with my back to north. And this isn't working. What's going on? I'm going to have to stand next to my computer. No? These cactus.
Did you break it?
No. Now I'm going to have to press the button. There we go. Okay. Now, I guess most of you probably have seen stellarium. It's very useful, but I don't know if you can get it for a phone, but it's particularly good for a computer. And you can use stellarium to show more or fewer stars. So depending on where you are, you can turn up and down the stars and the background. You'll find that if you have too many stars up there, you'll be completely confused because you will see 4 from up above you, and same way around the other way. So you can change that as you like. I tend to prefer to look south because when I'm standing on the astrofield at LDSS, I'm looking southwards to see the octaves. So I generally do that. Turn the thing around. I like to have north. Southward facing north is kind of behind you if you sort of bend over backwards. And it's exactly the same. Now, watch Orion's belt stars. You can see Almanac. Look at this. Almanac is right on, with the belt stars are all right on the equator, so they will wander right across down to the west tomorrow morning. And there it goes. You see that? It's setting in the west now. So it's moved along there. That's the equator. And it doesn't go directly above us, but well, it does if you're on the Earth's equator. Now, you can get more detail about stellarium, and through that orientating yourself, you can turn on the equator. I've already done that. You can also show the meridian, which is the north-south line, which all these stars pass at their culmination. You can mark the zenith, which is that bit, straight up, and there is a Z in the middle, that's F. You can mark the south celestial pole, which is the point at which everything goes around. You didn't know that. Get out. And everything does go around the pole, and you can prove that everything goes around the pole because you can bring up the paths and that they're all are. So that's the direction of all the stars go. So that's how the stellarium star map works. Okay. You can also show constellations. Now, part of these talks are for experienced astronomers like me to stand there and say, "Oh, Quill's over there, and Musker is over there," and stuff. I've got a computer to do that for me because I can't remember them. There they all are. You can even bring up their names and it gets very, very busy, so I like to kill it off. Right. You can also show deep sky objects, and deep sky objects are exactly the same. They can follow the Milky Way, but not always does. Again, they make it very, very busy, so I like to turn it off. So, all right. Quick bit on what you need. You're going to need dark adapted dials. You're going to need your chair while you're gone. The notes for the night, I can never ever remember without notes, which are down there, what I'm supposed to be looking at throughout the night. It's very, very important. Turn phone notes down. Now, equipment, any one or all of these. I've got one of these. Actually, I've got one on the other side as well. Binoculars are great for viewing. Eyes are even better actually, but binoculars are really good. We find that when we're doing science with people, we find that people, when they look through a telescope, particularly on high magnification like sheer cassegrain, they're looking at something up there, and then they move away from the telescope and they go, where is it?
Yeah.
There's no communication or there's no relationship between what you see with your eye and what you see with a telescope. With binoculars actually bridge that. You can say, oh look, I can see this in the binocular, and then once you take them off, you can see what you're looking at. So it's very, very useful. Binoculars are great. Make it low power, high aperture. You can get a small telescope. Small telescopes are great for young astronomers who are not grumpy. Make sure you don't get a hobby killer, because that will, as the term goes, kill the hobby. But a good small telescope is very useful, particularly for planets and clusters and things like that. You can get a high magnification telescope like Schmidt cassegrain, which is really good for planets, not so great for clusters because you see a star. Unless it's a really small cluster, of course. Don't try to play it. Then you can get the large aperture telescope, which is great for nebulous as well as dark things, particularly in dark space. So grab your dog and go up to DSS. Actually, even better than that, have a look through the Philips telescope. So finally, what's in the sky? For the selenologists, the new moon is tomorrow, and LNDSS is kind of at the moment. So you won't be going up there. However, over this week we'll be seeing the moon setting in the west in the evening, and the lunar X. Who's seen the lunar X? Who knows what the lunar X is? Oh, okay, you're in for a treat. The lunar X is available on the 18th of January at 5 minutes past 8. So give it a go. It's actually going to be seen. You're going to be able to see it. It's about sunset, so you'll need to be having a pretty good look. But yes, 8:05 p.m. on the 18th. What is it? I'll get to that. I've got a photograph. Okay, so by mid-January, the moon's high in the sky after dusk, and it's rising after sunset. By late January, that's the time of the full moon. Don't bother looking at the full moon. It's not very interesting. It's much more interesting when the lights at an angle. And it's in early February. It's going to be a morning object, so you're going to get up for that. But there are features on the moon which you can only see in the moon, so it's fun. Now this lunar X thing, that. You can see that for about 45 minutes, possibly 3 times per year. This thing here is it's called a lunar V. It's sort of a lunar X's sort of fourth cousin. It appears at about the same time. Well, it's quite an interesting little thing, and that's my photograph. So thanks. Okay. Back to the sky at 10 p.m. facing south. General sky, major targets, and what we're going to do over next month. I cannot ever remember stars or constellations. I have a computer and a phone. I don't need to do that. We don't need to do that. It's the 21st century. However, I do know things like the Southern Cross. Southern Cross at the moment is kind of 7 o'clock when you're looking south. It's down there. And let's see, over the next month, it's going to do that. So by the time, in 4 weeks' time, it's going to be sort of around 8 or maybe 9 o'clock-ish. So it's moving around. Orion is currently east of the meridian. Hasn't crossed the meridian at 10 p.m. yet, but it's pretty good for viewing right now. So it's one you should have a look at. By this time next month, it will have just crossed the meridian at about 10 p.m. So it's still going to be in prime position for viewing. It's going to be possibly even better next month because you don't have to do a meridian for halfway through your observations. The bright stars, there's a nice little spot of bright stars at the moment. I think that's one up there. And then and it's serious and prosine. My pronunciation of these stars is irrelevant. So if you know the bright stars, you can kind of find the dim ones. So it's useful to know a few of them, but I again haven't found that for that. These are going to do weird things over the next month. Yes, I'm going to speak. That's fine. They will come back. They will be here next year. Hyades and the Pleiades are another one that you always remember. You see it's that V in the Pleiades. They're right on the meridian just at the moment. In fact, what time is it now? I don't know. But they'll be very close to the meridian. So try and viewing if you can get it. Look at it tonight. Tonight will be probably Jupiter. They are going to continue getting, and they'll start to get low in the northwest as the year rolls on. The other crosses, there's the Diamond Cross and the Diamond Cross and the False Cross. The Diamond Cross and the False Cross are prime viewing areas, really full of all sorts of interesting things. It's a good chunk of the Milky Way of the Emu. So that's the reason why it's just chock full of interesting stuff, and that's starting to come up. So, so it's when it went very low, it's less interesting to look at. Now let's see. Saturn is down there, and it's getting very low. I think it's actually. I understand that it's probably a little bit too low for us social income. So goodbye Saturn. In fact, this time next month, it will be below the horizon. Jupiter is still good, and will be probably tonight. And it's going to be moving towards the horizon. It's marching. I think it's in prograde at the moment. Someone will correct me if I'm wrong. No, okay. I assume I'm right then. Now let's see. Suggested targets. This is the interesting bit, and this is where just one of millions of different suggestions. However, my normal strategy is I start west and I move eastwards, but I do it in chunks, so I'm not swinging the telescoping deck all over the place. It makes it hard work. So I can start, if I can, if you've got a decent view of the horizon, have one last look at Saturn, because it's cool. But then there's Jupiter, obviously. We'll probably not look past that tonight. Pleiades is right next to Jupiter, or close to Jupiter. Pleiades is an open cluster, and you don't need a big telescope to see it. It's just that little cheap non-hobby-killer telescope is really good for Pleiades. Don't make it too much magnification, because the Pleiades is gigantic, and you'll need a long photograph eyepiece to get it all. Pyridani, which is cat-size double. Again, you don't need a big telescope to see this. The doubles are really good; they stand out nicely. It's on the other side of the sky. It's very close to Achenath. It's actually easy to find. So it's a good one. Not very far away from that is 47 Tup, which is a blob. Now you'll need a little bit more aperture to see 47 Tup. It's next to the small metronomic cloud, and it's also not very far from Beta Tucano, which is a double. It's another thing which is easily viewed with a small telescope. Sorry, it's a true. That sounds like Harry's voice.
No.
It's not. All right, it's a double and a half. I'll go half. Okay. Tarantula Nebula is around. It's pretty good at the moment. It's close to as good as it gets. You will kind of need to be in a darker sky site. But up from LDSS, I've seen it with a 70mm refractor little hobby killer. It's quite fun to play around with. And yes, you can see it from a dark sky site with a very small aperture telescope. Obviously, the more the better, but the tarantula is really good for its full filaments. Diamond cluster is not very far away. Again, it's in that Woodland diamond false cross actually area. It's very pretty. Moving across the sky, you can't do any observation without looking at M42, the Great Nebula Orion. And if you've got a good sized aperture, it's great. If you don't have a good sized aperture, but you do have a lot of magnification, say you've got a little Schmidt Castle or something, check out the trapezium in the middle. Trapezium is a bit of a misnomer. There's a lot more than 4 stars in it, but it's a really, really small cluster. So, and if you've got a big nebula, if you've got a big nebula chaser, a Dr Tsana, the flame nebula, you might be able to see that as well. So that's what I'll be doing in that area. Then, probably more for the astrophotographers, move across the Rosette Nebula. It's gigantic. It does have a cluster inside it, so that's if you've got a big aperture, you'll be able to see something about it. M41 is a little beehive. It's an interesting little cluster, well, interesting big cluster actually. It's very, very busy. So you'll need a low magnification telescope to see it. The trick about seeing open clusters is you need to have a magnification which is low enough to get dark around the outside, because otherwise it's just some stars. So it doesn't look like a cluster unless you can see something which is not a cluster. Southern Alberio is not very far away as well, and that's one of my favourite ones. It's really cool. It's different colours. It's great fun. And if you want to stretch goal, M46 is an open cluster, and inside it there's a little planetary nebula. And I actually got a photo of it last week, something like that, and it was just an accidental photograph. It showed up really, really nicely. So I don't know whether you can see it in a telescope, but you're going to need to have a fairly large aperture. 40 inch telescope to LMD6 will probably get what you need. If you wanted to ditch the telescope, there is the Alpha Centaurus. Theoretically, at the moment, I think they've got about 1 every 15 minutes, so it's but if you wanted to ditch the telescope and grab a binoculars, a bit of practice is see if you can see Sigma Octantis. It's a real challenge. The astrophotographers will probably be able to help you out there. I can. If you can see Sigma Octantis, you're going to go. And also, think about where the Milky Way is. It's sort of there at the moment, but it's going to be moving around all over the place. If you're outside of Melbourne, you'll be able to see the Milky Way starting to come up about that. So it's starting to come into the system. Tomorrow morning, just briefly, I won't go too far in this. Venus is boring as anything. It's waxing gibbous at the moment, which is pretty much all it does. It goes through phases. It does look very pretty when it's a crescent, but otherwise it's just a white form. Mercury is the greatest elongation in about 3 days' time from now. So that's prime viewing time, but you have to get up in the morning for it. It's fairly good. So it is actually about, because it's greatest elongation, it's about a planet at the moment. So you need a fair amount of magnification to be able to see that. Mars, forget it. But Orion is setting, so Scorpius is rising. I love that moment where you can stand there and say, there is Orion, there is Scorpius. It really makes you feel as though you're in the sky. I climbed the mountain once in northern Norway in mid-summer.
Do they have mountains in Norway?
They have. And it's rather fun to see the stars in that. It's really cool. So then you really do understand that you're standing on a wall just spinning. Anyway, that was a tangent. Carina Nebula is, if you want to see Carina Nebula tomorrow morning at 5 AM is a great time to do it. It's right on the review, so it's in prime place. Okay, how to find out the types? I think I'm going to rattle through this. Carter steel and computer stuff is what we want. There's lots and lots of them. You can use planispheres, and here's my Northern Star. This is my guy. Because that's mine as well. It says Bill Stent on it. So there's ASV rock. There's you can see there's even page things. Right. Anyway, so there's the Facebook pages. Kate Green does this stream. You probably get 3 or 4 email posts anyway from Kate every day. They're really good. Email feeds. I'm on Earth Sky News, which is American, but it's kind of good anyway. Obviously, there's Crux. They've got the What's in the Sky section, and if all those fails, ask someone. Me, for example. Final words. 28th of January, at 6 a.m, Mars and Mercury are going to be right next to each other, like almost touching. Extremely low in the east. It's going to be very, very hard to see. It's a very, very good conjunction. Sunrise is about a half an hour afterwards, so it's going to be a major challenge. You're going to need a really good view to the eastern horizon, but it'll be worth it. Going to put the lights on? Yeah. You can put the lights on. Oh, jeez.
That's why I can't get one.
M1, the Crown Nebula is low in the north. It's about as good as it's going to get. Who's seen the Crown Nebula? It's really good. Who's watched it over the last 20 years? Have you seen that video? There it is at astropin.com, 3, whatever it is. Somebody took a time lapse over 20 years of the Crab Nebula, and you can see it expanding. It's unbelievable. Yeah, it's really cool. 27th of January is first of all my 60th birthday. Second, Uranus is stationary and there's a full moon. This is true. But tonight, Jupiter is hiding its moons. Ganymede is going behind the moon, and then Europa is going to go in front but not cast a shadow, so it's going to disappear. And then Leo is going to go behind, and so you're only going to see Callisto. So I think Ganymede is going to come out about after midnight, so we probably won't see that. But so yeah, tonight Jupiter is going to look kind of odd because it's going to have moons missing. So that's it. That's all I have to say.
I said you got planetary vision range sources as well.
You got it?
Yeah, it didn't need to. Yeah, it's turned up.
Well, it's there.
Yeah. Didn't know it was there until I processed my images. It's like, oh, there's a planetary. It's good. Well worth looking at, and you can definitely see it from 40 inches as well. As Bill said, perfect blue skies, new moon, but the site is closed for the time being. It will reopen after Australia Day long weekend because there is a lot of damage on site. We were flooded last week and kind of cleared it up, so reopened safely, and then we got hit with 2.5 days of, it was 250 mil in 2 days or whereabouts up there. So, in 1 day, it was 2.5 days. Yeah, so close to 300 mil fell over that from Sunday to pretty much yesterday morning. Clobbering got flooded again. All the pathways that we've redone and re-gravelled got washed away again. All the drains are all full again. The pathway, the gravel, the allability pathway towards the radio dish, if we don't fix it, it will subside and fall. So there was a lot of work that needs to be done on site. The astrophotography field is a swamp at the moment. You could have gone swimming there on Sunday. It's that bad. So we've telescopes, yeah. We wouldn't get polar alignment, that's for sure. Yeah. Every time you get it, just driven the leaning tower of telescopes. So we decided to close the site so we can repair it, so we can have a big working day straight over and we can, we're hoping to get all of that and other things rectified on site to make it safe that when we go back to it. But thank you for joining us tonight. Thank you, Bill Stent, telescope. Looking forward to continued progress.
Next one's will be shorter.
That was all right. And thank you, Dr Tsana. I'm not going to try and say it because I'll get it wrong. Thank you very much for your talk. It was wonderful. The video was live. So if you really want to watch it, you'll be able to see it on our YouTube channel tomorrow once we upload it. And thank you everyone for coming. Stuff will be served, and then Bill's going to run over to the trout seals and get it set up, and
I'll get Jupiter for
Kevin's going to go and set up the 10-inch, or
I'm going to get to that.
I'm setting up the 10-inch. Are we doing the 10-inch? We're doing after the 10-inch. Alright, cool. We'll see you guys out there. It's nice looking good. Thank you for coming.